YouTube. And once this is done, we can finally start. And meanwhile, people are joining, so it's 1 minute delay that we got. It's positive.
Okay, sorry. Just let me know when you want me to start.
Yes. Okay. So I'm very glad to announce the talk of Steve Miller on Eulerianity, Eisenstein series, and Arthur conjectures. And as you can see, Steve has started to talk on the seminar a long time ago, and we're really waiting for you, Steve, to appear here physically. So far, we are glad to have you here remotely. Yeah. Please start.
Okay. Yeah. So, I mean, first of all, I just want to thank Dima. It's really, I just look out and see how many, what a diverse group of people from all over the world are a part of this local seminar now. And I see you've taken a really challenging situation of isolation and you've been clever about it and turned it on its head. It's the exact opposite now. And we have a big challenge in America and all over the world to bringing in different diverse groups of people into mathematics who haven't been as involved as we really need them to be. We need to bring in all the talent, and hopefully this will be inspiration for us to be more clever in how we go about that. Anyway, you certainly don't need to hear from me, but as you said, I've been there before, but nevertheless, I'll keep going. Weizmann was the first place I was at in Israel as a kid. This is on Rehov Eisenberg, down the street from Steve Gelbart, and it's always been my home when I, from then on, and when I come to visit Israel, it's a place people have been very friendly to me. So I really hope to see you all soon. Okay, here we are. So some of this, some people have heard, we had a workshop at Rutgers, but let me just give an overview. I really want to have a goal here to explain a topic. Not, there are some results in the topic that I want to explain also, but I'll be happy if at least I can get across the thrust of the problem. So we're interested in the unitarity problem, but we're going to be interested in just a particular aspect of it. So the unitary dual problem, say for a real reductive group, is to fully describe all the unitary representations. And that's a very hard problem. Now, what do we know? Well, you could first ask about describing the irreducible representations, and without going into the history, this is something that's long been understood in various forms. But the really hard part is to understand which of them have positive, definite, invariant Hermitian forms. And this, if you've ever looked at this in any detail for examples, you see very quickly that it's pretty complicated. It's hard to, there isn't even, as far as I know, a firm conjecture is what the answer should be, much less a proof in many cases. So one can ask, and this is something I learned from David Vogan, was to really emphasize the particular subset of the representations, which say might be enough for applications like automorphic forms, say as a beachhead towards understanding the unitary dual. And these are representations of Arthur predicts. These are unipotent representations. So I would like today to really talk about these unipotent representations and explain in the context of, say, exceptional groups what they're about. By the way, Dima, I realize somehow the way I have this set up, I don't see the clock. So you should tell me when I'm getting, say 10 minutes to the end or something like that, which I think is not yet.
All right.
Okay. So, why did I get into this? I think actually last time I came to Weizmann, I spoke about automorphic forms that came up from string theory that related to this. Today, it's really more about real groups, not the global picture, but I do want to spend some time talking about why this has become a watering hole for many different types of scientists now. Also in algebraic number theory. And the another reason why the unipotent representations are so important is that they're thought to be in some sense, which I haven't seen completely explicitly written out, say enough as a conjecture, but they're thought to be the building blocks of the unitary dual. Or certainly a lot of the unitary dual should, in principle, be understood once Arthur's unipotent representations are understood. So that's why we look at these. No, okay. So to begin talking about Arthur packets, we need first to talk about Arthur parameters. So I'm going to look at split real groups. The logic behind that is that usually when you look at unitarity, the split groups are the hardest case. If you go to the other extreme, you have compact groups, everything's unitary. And it's just a lot easier to state things if we look at split groups. So we have G, which is the split real group, and we have the complex dual group. Okay, so here if I took G to be SL2R, that would be PGL2C. And then there's the Wavefront group. So the Wavefront group is basically two copies of the complex numbers with something that acts like complex conjugation. Algebraically, it's very easy to write that as something inside the quaternions. J is the usual IJK gadget in the quaternions. So Arthur defines parameters as certain types of maps from SL2C cross the Wavefront group into G check C. And there's certain criteria this has to satisfy. So at first, this looks like it's a very general algebraic thing, but in many ways, it's also combinatorial. So the homomorphism has to be algebraic, which is a big constraint. And there's also a technical boundedness hypothesis. I'm not going to state it because it's going to be automatically satisfied in everything that we do here today. There's a notion of unipotent Arthur parameter. So unipotent Arthur parameter is one which is trivial on most of the Wavefront group. It's trivial on the C star factor. So what does that leave us with? Well, psi of J squared has to be 1 because -1 is a complex number. J squared is -1. So the image of J from the Wavefront group here is an order 2 element, or maybe order 1 element inside this complex dual group. And then, well, what's left? In order to be a homomorphism, these two factors, the images of these two factors have to commute on the other side. Otherwise, it's not a homomorphism. So what this amounts to here is we have an order 1 or order 2 element psi of J. And then inside, that lives inside this complex dual group. And then there's also an algebraic SL2C that commutes with it here. For example, if psi of J is 1, it doesn't give any constraint on the other than being algebraic for this SL2C. So there's basically two aspects here. There's the order 2 element, and then there's this little SL2 that's sitting nicely in an algebraic way inside G check C. So what does it mean? What does it mean that, what is this SL2C doing here? I mean, Langlands parameters are really about the Wavefront group, and what is this SL2C coming to tell us? So like anything, there's various opinions. So one thing I've heard a lot of people say is that it tells you how far away you are from being tempered. And I'm not too satisfied with that because there's non-trivial examples where you have tempered representations, even though the parameter looks like you're pretty far away from being tempered. Maybe that's something we can talk about later, but at least that gives some indication of what it means. And there's another one, which is my own favorite one, which is that it sort of tells you how big the representation is. It's related to a wavefront set. And I can later be more explicit about that. And so this is really important in terms of saying things about non-vanishing linear functionals on a representation. Okay, so just to summarize the slide, an Arthur parameter is an order 1 or order 2 element along with an SL2C that commutes with it. So I'm gonna have a problem going from one slide to the next. Okay. I don't know why. I always have this problem. It's a new computer and the same problem, so I guess it must be software. So I want to now say more about this SL2C. And so that gets us into the topic of nilpotent orbits, which is more or less Jordan canonical form, say if you're in the case of SLN, for example. So the Jacobson-Morozov theorem tells you that if you have an SL2C, or really the Lie algebra variant of it, you can think of it as a triple of the standard generators of the Lie algebra, and any nilpotent element can be completed to such a triple. So it makes sense to look at the image of a nilpotent element in SL2C. So the D here is just the differential because it's on the Lie algebra level. So this will be mapping a nilpotent element to a nilpotent element in the dual Lie algebra here. And that will live in some orbit. There's a number of, there's a finite number of nilpotent orbits of the complex dual group acting on its Lie algebra. These are often called coadjoint orbits, but actually they're adjoint in this case. So the image of this SL2C, the group SL2C, gives you on the Lie algebra level a little SL2, a frac SL2 triple. This will be the, say we call the positive element, so the upper triangular one. And then there's a neutral one, which is the image of the diagonal matrix 1, 0, 0, -1. And I'll call that 2 lambda for now. 2 lambda lives in in the carton of the dual Lie algebra, but just by the construction of the dual Lie algebra, this is spanned by, basically it's equivalent to the root system, the root space for the original one. So I can really think of 2 lambdas being a linear functional on the carton of the original group. Okay. Okay. So anyway, so just to be more precise, this one other way to say it is that in terms of nilpotent orbit theory, you can look at a nilpotent orbit of the dual Lie algebra, and it has a weighted Dynkin diagram. That weighted Dynkin diagram is just telling you the inner products of this neutral element against the co-roots, which are really roots because it's dual. And so the weighted Dynkin diagram is determined by this 2 lambda, which is really a linear functional in the original Lie algebra. So now Arthur parameters are taken up to conjugacy, so we can refine this a little bit. Before I said we had an order 2 element and an SL2C, but really I could just take the order 2 element, and then I could look at nilpotent orbits, but not just any nilpotent orbit. It has to commute with psi of j. So I need to look at a nilpotent orbit that's in the +1 eigenspace of the adjoint action of this order 2 element, and that's a symmetric subalgebra of G check C. Okay, so this orbit carries a lot of information, as I was hinting to before. The orbit, first of all, it's telling you really what the SL2C is. So you can now just replace, as I said, you can replace Arthur parameters not just by homomorphisms, but really by order 2 elements and then certain orbits that meet things they stabilize. And it will turn out later that if we look at the Spaltenstein dual of O check, that will be more or less the wavefront set. I'll try and be more precise about that later. And that's a very important invariant in automorphic forms of a representation. Okay, so that hopefully explains what an Arthur parameter is. Happy if people interrupt with questions. And then the next thing to talk about once you have a parameter is what's a packet. And then life gets much more complicated very quickly. So Arthur predicts a packet enlarging an L packet of interesting representations, and they have very very important properties, but perhaps the most important, most intriguing of which, and the hardest, is the unitarity of these representations. The question now is, how do you define the packet? So Arthur's statement that predicts the packet, as far as I understand, predicts that there is a packet which satisfies a stability criteria. I don't want to go into that criteria now. So this is in a series of papers refining the conjecture in the mid to late 80s. And then Adams, Barbosh, and Vogan, I think it was published in 1991, but maybe the work was a few years earlier, gave a definition for real groups of packets. And that's, of course, a lot of my work here, I'll explain, is joint with them and other collaborators, so I'm following their definition. There's no contradiction between the two. There's work relating, for example, they prove the stability, and there's other things you could do with that. But I want to point out something that I think is a little counterintuitive to the automorphic forms community. There is sort of maybe a little slogan going around that you've defined an Arthur packet if you find something that's stable, but there actually are stable combinations other than the packets. So in other words, stability isn't just enough to really pin down or to define a packet. It's a property that packets have, but it's not. It's a necessary property of a packet, but it's not sufficient to nail it. Okay. So so a lot of this talk is about what's in the packet. How do we actually figure out what the representations are? I mean, these are supposed to be really interesting objects, and we'd like to get our hands on them. So there's one representation in each packet which you can define, and Arthur did, and it's often referred to as the Langlands element, or maybe base point of the packet. And I want to explain what that is. It's basically the idea is that you have this SL2C and you have the V group, and you define a Langlands parameter, which is a homomorphism from the V group to G check out of it. But in more pedestrian language, I introduced in the previous slide lambda, which was half of the neutral element of the SL2C. I mean, this was also the weighted diagram of the orbit, or half of it. And then there is a quadratic character. Well, there's a quadratic character implicitly defined on the original group, on its torus, I should say, by the order 2 element. This is local Langlands for tori. And so you could take, you need to make lambda dominant first, but you could take a principal series for lambda that's induced from lambda and then this quadratic character. And then you could look at it, and it has a quotient. Now the problem is it may have more than one quotient, maybe, but there's the Langlands classification handles this, and there is a definition of the Langlands element of the packet. Okay, so we have the situation where we want to have packets, and there's only one thing which we can really explicitly identify in the packets by the definition of the packet themselves. And these packets can get pretty complicated. I mean, it's another suggestion floating around is that the Arthur packet should be a good basis for doing harmonic analysis, like Plancherel type things. But there's a problem because the Arthur packets have non-trivial intersections between them. So that I will address that in a bit later. There's a notion of weak packet, which is in many ways more useful for what I want to talk about. And that's just simply what you do is you take the union of all the packets which have the same Arthur parameter. So that weak packet is indexed by an orbit, right? Sorry, I said that wrong. Packets are indexed by an Arthur parameter. Weak packets are the union of all the packets with the same lambda, but maybe different order 2 element psi of j. So I'll have some slides with examples of this later. So weak packet, if you just want to show these are unitary, which is the last remaining major question about them in some sense, other than identifying them, then this is just as good. If you can compute weak packets but not figure out stability or whatever it is that defines a packet, or doesn't define a packet, I should say, then this is great. And now the major new thing, and this is the work of the Atlas team. So this is Jeff Adams, David Vogan, Marcvan Leeuwen, and Annegret Paul, who I think are all here and are poised to correct me and improve what I'm saying. But they've developed a method to compute weak packets. And this involves a lot of their older work on, which you may have heard of, with Kajan-Lustig polynomials and cell computations. And there's also some newer things that have gone into it with character tables, which is, and it's maybe find ways to compute things that would take 1,000 years if you don't have to do it cleverly and try and get it done in human time. Okay, so I'll come to say more about the computation of the weak packets from the Atlas point of view, but just to highlight this is now something feasible to do. Maybe slow, but feasible, is to compute the weak packets. Any questions? Okay, so I promised I would say something about the wavefront set. So the problem is that say this carefully, take a lot of time, at least for me, to get it right, because it depends what field you're working over. There's an issue with the algebraic closure. But any irreducible admissible representation has orbits attached to it. If you're thinking of the orbits over the complex numbers, then there's really only so there's that question that, okay. Sorry, I screwed this up. There's one sort of complex orbit, and there could be multiple real forms of it. So here's a list of certain orbits that are interesting to look at. So Dima and Siddhartha Sahi have been writing a lot on this, and a number of physicists have become interested also, like Daniel Persson and Axel Kleinschmidt. You could have something called the associated variety of the annihilator ideal. So roughly speaking, the annihilator ideal is everything in the enveloping algebra which kills things kills the entire representation, and that by algebraic geometry carves out a zero set, its associated variety. Why this is completely stuck now. Oh yeah, okay. So the big theorem, which I believe is due to Tony Joseph from Weizmann, is that this is the closure of a single complex nilpotent orbit. So this is maybe the simplest one to talk about because it involves just one orbit. So basically this orbit O is associated to pi. Every pi has an O attached to it. And it tells you a huge amount of information about the representation. So it controls, say, if you have an automorphic realization, that many of the coefficients vanish, which is pretty striking. And it tells you the Gelfand-Krylov dimension of the representation. And then there are these two other real orbits called the associated variety and the wavefront set, which are related to each other. I believe by Worker Schmidt and Valonen. And here, the complex orbit basically could break down in terms of a number of real orbits, and that's finer information. And you can define packets precisely in terms of the lambda, which is the weighted diagram, and a subset of the real forms. Let me not go into that here just to keep things simple. It's easy to explain a weak packet now. A weak packet is every irreducible admissible representation of G, of GR, this real group, with the particular infinitesimal character lambda. Lambda, remember, comes from the orbit's diagram, and the associated variety of the annihilator ideal is this dual O. So remember, I defined lambda in terms of O check. I should have written that here. And the associated variety of the annihilator ideal is the Spaltenstein's dual. So if you take all the things with the same infinitesimal character and same size, so to speak, that's a weak packet. So I did write it. And then so why do packets intersect? Well, that has to do with these different real forms of it. Some might be shared in common. So right now, the situation with Atlas is that it's completely doable to compute weak packets, but computing packets of big groups is hard because this is a very tricky issue to resolve. Okay. So this definition of weak packet gives us more of a flavor for what the Arthur representations are and why they'd be interesting in automorphic forms. The representations are small. See, this orbit may not be so big. It's generally not, these are generally not generic representations. And so you have things like minimal representations and other small representations that come up. And those are really interesting in terms of number theory because you have these sequences of vanishing coefficients. And it's sort of like a high wire act. You can manage to make something as complicated as an automorphic form from so few coefficients. And these are things that are used in constructions all over the place, like in L functions and theta lifts. It's really sort of bread and butter automorphic forms at that point. I want to make the point, though, that the ones that people looked at in number theory are just a very, very small corner of the total number of unipotent representations. Okay, so any questions? Right. Okay, so now I'm going to focus on split exceptional groups, and the reason is that Arthur, I think that certainly he's handled the split classical groups in his monograph on the trace formula, and I think there's a lot of progress also on the non-split ones. And this is via the fundamental lemma. The flavor is really different anyhow. So first of all, the split exceptional groups weren't treated by Arthur, but there's a major difference. There's an issue of a component group. So if you look at the image of this SL2, you can ask what in the group centralizes it. And that group in the classical case is always an abelian group. And that there's a huge influence of that in terms of the packet structure. For exceptional groups, this group is very often very far from abelian. I'll give you an example later where it's S5. And so the types of issues that come up for exceptional groups are just not seen at all in the classical setting. And there's also the phrase Steve Rollis used to like to say, if you could do something for E8, you can do it for any group. So I want to sort of understand this for E8, and then that's why I'm going straight to exceptional groups. So first of all, you can ask, what are the parameters? And so the parameters, as I presented before, had a short definition, but it's not too easy to work with it. So Joe Hundley and I worked out the list of all the parameters for exceptional groups. There's 341. And this component group is quite big in many cases. Okay, and now maybe the main result today is that together with the Atlas team I mentioned before, Jeff Adams, Marcvan Leeuwen, Annegret Paul, and David Vogan, we've now computed, well, I really should say a weak pack. This is not a correct statement. I shouldn't say we computed all packets. We've computed all the members of all the packets. We computed the unions of the packets, but we've computed all the unipotent representations now for exceptional groups. And I'll give you a census later. And the ones that you may have seen in automorphic forms or in string theory, for example, are very simple packets. They're singletons, and they're these pretty crazy looking packets that haven't been studied yet, and I think would be very interesting and hopefully have applications to number theory. Now, unitarity is the other big question, right? Now we have a list of the representations, and now we can start asking if they're unitary. So Joe Hundley and I, in some different papers, showed that the Langlands element, remember, that's the one representation Arthur explicitly mentions, is always unitary. And that was done using Eisenstein series. And in a few cases, we used the Atlas software out of convenience. The Atlas software has gotten very good at telling if representations are unitary on, up through E6, certainly. It's very efficient now. I think it can do done like in a minute or two, maybe. Okay, now Arthur is coming to this from a global point of view. And so there's sometimes statements in the local, the local statements are sometimes a little different than the global ones, but either way, there should be automorphic realizations of all these representations. And those should be really fascinating objects, and it'd be nice to be able to construct them. It would be nice to, at least for each unipotent representation, to give some automorphic realization. But that seems to be a hard problem because they might come up cuspidally. It's not so obvious. I don't know a general statement which predicts whether or not a realization has to be cuspidal or has to be Eisenstein. There are a few theorems in the background, but in general, we just don't know. I mean, Arthur predicts from the trace formula point of view that it has to occur in the discrete spectrum, but this finer information is not available yet. But in the future, we would like to see these realizations. These should be really interesting automorphic forms. Okay. Now, actually, if you look at this question of cusp forms versus Eisenstein series, the literature has several statements, and there's a paper by Gangrevich and Duajong, which I think settles this very clearly. And so if you decide to look into this for G2, look at their work first, because otherwise you'd be led. It's like watching a tennis game, a lot of back and forth. Okay. Dima, how much time do I have left?
You have about 40 minutes.
Oh, really? Okay. Okay, I meant in the talk, Okay, so this is now a list of the unipotent representations for the exceptional groups. I want to thank Jeff Adams for putting this nice list together. And so we've been working very hard to compute these over the last several months. There are 1,465 unipotent representations among all the real forms of all the exceptional groups. I'm happy if Jeff or David or Mark or Annegret want to chime in. Let's focus on my favorite one. So here, this is E8. So there's 362 unipotent representations here. And at first that looks to be a huge number. But it's actually, the big surprise is it's not so big. The analogous number for E7 is 276 or 252, depending which form you're on. And for E8, it's about a quarter of that. F4 actually has more than E6. Go figure. There are 70 or so orbits. I think it's 70 orbits for E8. So there's a huge number of parameters for E8. Most of the packets for E8, I think, are not so big. There's one that's pretty big. Remember, the packets overlap, so it's a little hard to measure it that way. The compact groups, this is just basically almost by definition, there's one packet. And then if you want to look at, say, a quaternionic form of E8, this is handled also. All these are written out. We have them on my hard drive, for example. We have a list of all these representations. And so, so from here, we can start asking other questions, like whether or not they're unitary. But I'll go into some more detail about this. So here's my favorite slide. This is something a lot of people have looked at from different points of view, including Gangrevich and Zhang and Gordon Saab and many people. I don't think I can be completely complete. Let me say it like this. So there's two packets. This is the only interesting case to look at G2. There's one distinguished orbit, which isn't the regular orbit. It's called G2A1. And there's two packets. There's two Arthur parameters. One has psi j trivial, and the other it's non-trivial of order 2. And the first packet has 3 elements. So Jonathan Fernandez computed this in his thesis a few years ago. These numbers refer to things you'll see in a second. So one packet is 3 elements, the other is 2 elements. And now I'm going to put a little picture of here what they look like. I should explain this picture a bit. So I have on the left and the right, I have 2 principal series at lambda, which is var pi 1. It's the fundamental weight for the short root. And I'm decomposing this principal series in terms of, I'll explain what the notation in a moment. And here's a second principal series, which I'm giving the decomposition of. And these principal series decompose into, the colors mean which number here. And the 9, for example, means what X is. That's the KGB orbit. This is in Beilinson-Bernstein, maybe not notation, but this notation refers to the Beilinson-Bernstein classification. So these are a composition series, and they each have 5 levels. The Langlands element occurs at the top of each one. The bottom is a discrete series. So remember, I said all the Arthur representations in the same packet have the same size. They're all pretty small in this case. So there has to be a very large discrete series. Well, it happens to be a discrete series, but it has to be something large. And that sinks to the bottom here. And what's amazing, of course, some of these can occur more than once in the composition series. So this one for 4, number 4 shows up 1 level down and again at 3 levels down from the top. But it also occurs in the other representation. In fact, representation number 6 occurs right below the top in the non-spherical one, but it occurs also in the spherical one. This is an important point because I think there is some folklore going around in automorphic forms that if you have a representation of a real group, it can't both live in a spherical and non-spherical one at the same time. And that's just nonsense. I mean, it does. And then there's this gray one is really interesting. It only occurs in the non-spherical one. And if you look very carefully, you see here it says 0, 0. What does that mean? That means this is tempered. So here we have a tempered representation in a packet which is supposedly far away from tempered, according to the the catchphrase that was circulating in the automorphic forms community. So the Arthur parameter is not telling you how far away you are from tempered. Maybe very often it is, but it's not exclusively that. And this happens, I think Jeff computed is one other example for an exceptional group where you have something tempered. It's on F4. I mean, there's always a packet of tempered representations from a trivial parameter. Yeah.
Excuse me?
Yeah.
So can I clarify
Sure.
The representations in the table, are those just components of spherical and non-spherical principal series, or do they claim that they live in some Arthur's packets?
Both. So I'll say again, the first packet is 9, 6, and 2. The second packet is 8 and 4. And the non-spherical principal series and its decomposition has 8, 6, 2, 4, and 0. And the spherical one has 9, 4, 6, 4 again, and 0.
So these numbers, what do they mean?
Well, the number 9, I'm just using it as shorthand to refer to which representation. The representation is input into Atlas by 3 pieces of data. One is a KGB orbit. And another is, these had to do with how theta acts on, there's an involution related to that, and it has to do with how it acts on the infinitesimal character.
Thank you. So there are altogether written here 5 representations only.
Well, actually 6, because there's a discrete series at the bottom.
Yeah, right. Together with the. Okay, thank you.
Well, thank you I'm glad you're here. Okay. So yeah, so Nadia and her collaborators, Wittek-Gan and Duazhang, have studied these and done really beautiful work about automorphic realizations. I think they have a very complete picture, and much more general. I'm only talking about real groups too. They have a very complete picture of G2, and I thought it'd be good to have a slide to explain that. So, I'd like to see happen is that great work for G2 that they've done be done on other groups. So there's 4 other exceptional groups, and they're as a first step, it's nice to be able to at least identify what the parameters are and what the packets are. Okay. So the way the way in the work of the Atlas team that we answer the question of what's in a packet is in this format, but this is a well-known way to classify representations through Valence and Bernstein. Okay, so now what G2 is somehow become very interesting to a lot of people recently, and I wanted to say more about that. So I've been involved in a project with some string theorists where they want to construct certain automorphic objects on G2 that come from rigid Calabi-Yaus, and if successful, that will be interesting because it's, I mean, I think it's highly non-obvious how you take something as unarithmetic as shouldn't say unarithmetic, but you start with a rigid Calabi-Yau manifold and somehow produce some number theory out of it through G2 would be pretty cool, and that will involve some representation similar to it. And then Aaron Pollock, who may also be with us, I'm not sure, has been telling me about some really interesting work, and also, which I mentioned, Eric Urban and his student Sam Mundy have also come to this from the point of view of algebraic number theory. So there's a lot of integrality phenomena on automorphic forms on G2. It's related to Shimura varieties and Galois representations, and to be able to give, be able to very explicitly describe how things happen on G2 automorphically is a value in applications in a very broad sense. The quaternionic discrete series come up quite a bit. And so you could start asking, well, what tools do we have to do computations with these? If you want to do something like analytic number theory, you really need to have a good grasp on special functions. And I want to mention there's been some work on that, similar to what we do in SL2. Aaron has a nice paper where he identified the lowest K-type for the quaternionic discrete series using Schmidt operators and differential equations. And he has many other tools. He's been writing a series of papers on on this topic recently, which I want to highlight. And since I'm at Weizmann, my student Joey Zhang and I have worked on another technique, which is algebraic, to use Wigner's theory of, basically it's a theory of spherical harmonics, and to extend that from SU2 to Maxwell compact subgroups of bigger groups. And from that we can do a lot explicitly on G2 in terms of the K-types, so you can compute intertwining operators and so forth. So this is just a bit of an aside, but I think it's maybe helpful for the community at large to know about, for example, Aaron's work and Johi's work. Okay, so back to the story of packets. This is probably, to me, this is the most interesting weak packet. So I didn't want to show you all, all few hundred of them. It'll look like a phone book, but there's a very interesting orbit for E8 called E8A7. It's interesting because it's its own dual. Its Spaltitzein's dual is itself. And it's also fascinating because its component group is enormous. Well, okay, that's not too big compared to, say, the size of the universe, but for this subject, that's a really big group. And it's highly non-abelian. It's the I think it's the only time there's a non-solvable group actually that comes up as a component group. The representation theory of the component group is important in understanding the subject, and there's serious complications for this example. So here there are 3 packets, and this again stolen from Jeff. Honest Arthur packet means really an Arthur packet, as opposed to one weak packet. All 18 of these together comprise a weak packet. So here one packet comes from the when psi of j is trivial, and it has 7 elements, and it has a spherical representation in it. And then the other 2, they're related to different. You can ask, what are the symmetric subgroups? They're basically different conjugacy classes of order 2 elements. There's 3, of course, 3, 8. We know this from Cartan's classification, and these are related to those 2. And I mean the last one in each of these is the Langlands element, and those we know that Joe Hundley and I proved are unitary, and we would like to know all of these are unitary. And there's 365 or so of these representations on E8. And the big question is, are they unitary? Okay, so just in fact, here are the big questions. So we really want to do is we want to identify all the packet elements, and I guess we've done that. We've done that now, but the real thing we want to do I mean, you might want to identify them automorphically and in other ways. We want to show they're unitary. And once we show they're unitary, we want to do more. We want to get other unitary representations in the unitary dual from that. And there seems to be really a lot of things that we can discover here in terms of number theory. So if you just think about how important theta functions have been in number theory, I mean, you have to say that's had an enormous impact all over the place. You can use them to get information about Gauss sums. You can do like David Ginsburg and David Sudre and Steve Rallis and Joe Hundley have, et cetera. They've done very interesting work with for exceptional groups of lifts using theta functions. Many other people, I mean, Saul Freeberg also. Could go on and on. And so one has to imagine that if you can construct the analog of theta functions, not just for one type of representation, not just for the small orbit, small wavefront set, but for all of them, you'd have a huge amount of tools you could really use in number theory. And then there's some other cool questions. So Arthur, one thing that I didn't mention much about is that there's relations between these packets on different groups. So Arthur mentions that presumably you can take a weak packet from a Levy of one group and induce it up to get the weak packet for another group. And that, I don't know if that's in the form of a conjecture. I don't know if it's completely known, but this is something which is completely accessible now if you learn what a packet is, or maybe it could help you define packets. So Atlas can do induction. It can be slow in some cases, but it's doable. We never ran into an induction we couldn't do, although some of them took a long time. Okay, so let me say a little bit more about this because there's a subtlety here. So if there's this parameter, and there's a difference between the parameter being distinguished and simply the orbit being distinguished. So what does distinguished mean? Distinguished orbit is an orbit which doesn't intersect any proper Levy. So there isn't a Levy which contains the element. And when you throw in this extra order 2 element, you might have an orbit which is non-distinguished, but yet there's no proper Levy containing the image of the full homomorphism because the order 2 element lies outside of it. Okay, I see there's a question here. No, okay, no problem. And so one thing that one would expect is that the Eisenstein series on smaller groups and things aren't distinguished are related. I mean, there's some automorphic induction from one level to the other, maybe via Eisenstein series. And this is another fruitful direction which could be looked at. I mean, these are all things you can do once you have a list of examples. And then of course there's unitarity. If you have unitarity on a smaller group, you can expect to try and get unitarity on the bigger group via induction. And this is something which I don't know any general proof for, but which Atlas can do case by case. And it's that's been part of proving, that's one of the techniques used here to prove unitarity. Okay, and then there's also in another direction, I was just talking about parabolic induction. There's also cohomological induction, which is much more flexible in some ways and can be used to prove unitarity results. So this is maybe a highlight of what future work will be. A lot can be said from the Atlas software, but I think there's also a lot of opportunity here for better theoretical understanding, which can be obtained through using the Atlas software to get data. Okay, so I have a few slides left. In case you're worried. Okay, I think okay, a few slides left. How much time are we? Oh, okay, about 15 minutes, I think. So I want to say something about what's been used in the proofs, and what the key thing I've been involved with, has been Eisenstein series, and I want to mention the history of that. So what's interesting here is that you get interesting Eisenstein series from Arthur representations, but you can also prove interesting things about the representations from them as well. And this was first done by Langlands. So Langlands did a very long calculation for G2, and he discovered the first interesting unipotent representation. He found the spherical unipotent representation. This is what I called 9 in that table I had before. And he has this amazing quote at the end. The reader will be losing heart. He is urged to persist, because the result is very simple. I do not know the reason, okay? And I'll borrow from the political statements of the day. Birgit Spey found really a major enhancement of this, but a major breakthrough, at least from my point of view, of constructing many new unitary representations from the point of view of Eisenstein series. I think that that's a very key idea here. And I'm just following in her tracks. We can use when we're able to do computations with complicated Eisenstein series, by understanding them better, we can get new unitarity results. And so how is that done? Well, we basically have to understand why there's all this cancellation. Langlands says he doesn't know the reason for G2. G2 is a sum of 12 things. For E8, you can have a sum of about 700 million things. And I met some remarkable physicists. Michael Green, who's the Green of Green-Schwarz, came to me once and said, well, I've got an example where the 700 million terms will collapse to 2 terms, and here they are. And I said, how do you know that? He said, well, I have intuition from string theory. That's a whole other talk. And he was right. I did the computation. I figured out an efficient way to do it. It was exactly what he said. So then I got to realize these guys, these string theorists, they seem to understand something about number theory that we don't. They seem to understand some asymptotics. And that led us to realize that a lot of interesting Eisenstein series were L2. And then once you think they're L2, you can kind of check that. And then that led to a new type of argument that was very different from Langlands. It's much simpler than Langlands for this purpose, I think. Somehow, from this intuition from string theory, out of this came a proof of the unitarity of one of the, maybe the representation which was probably hardest from, say, the point of view of the Atlas software at the time. And this is simply from the, proofs aside, the intuition behind this is very clear to, I think, to some string theorists, because they understand how graviton scattering relates in different dimensions. So there's something really deep going on here, which I can't even begin to get into. I don't understand. But if you looked at the point of view of the smallest representations on E8, the spherical ones, trivial, of course, was long known, and minimal was handled by Ginsburg, Rawls, and Sudry using the Eisenstein series. And the one after it comes from, and as well as these, of course, also come from ideas in physics. So I was able to handle all the spherical ones, spherical unipotent Langlands parameters. These are all the spherical unipotent representations. They have psi j trivial, boiling down to some properties of the zeta function, and a not such a bad calculation. And Joe Hundley and I then turned to the non-spherical ones, and here the situation is much more complicated because they're intertwining operators. And this handles the unitarity of all the Langlands elements. So this is the unitarity of all the representations Arthur directly predicts are unitary. I just want to say a little bit more about that. So what is going on even for SL2? So Eisenstein introduced these Eisenstein series. It's amazing how much this guy did in the 28 years or so he was alive. Pretty remarkable. There's a non-holomorphic analog due to Siegel, which is more or less putting absolute values in. And this is automorphic for SL2Z. There's no weight, and it's periodic in the X variable. So we can write a Fourier expansion, and it's a standard calculation in number theory to identify all these coefficients. There's zeta functions and divisor sums and Bessel functions. And this series diverges when S is 1. It has a pole there. And you can look at the residue at S equals 1. And all these terms are holomorphic at S equals 1 except for this term in the middle. And the residue there, this will give a constant times y to the 0. And in other words, it gives a constant. So there's ways to obtain the trivial representation through Eisenstein series for SL2Z if you understand the constant term and how it behaves at singularities. And this is much more complicated for other groups, but this is the idea of where the unitarity ultimately comes from. Another way to say it is that you're putting the unitary structure on the representation by first embedding it automorphically as an Eisenstein series, and then using the L2 structure. L2 has unitary structure. Okay. Now, in general, Eisenstein series are defined in a way that's a fairly straightforward generalization of principal series. I'll just write it for spherical ones. They converge in a certain range. So we take the standard line bundle definition of a principal series. As long as lambda is bigger than rho, this series converges absolutely, and it has a meromorphic continuation, has a bunch of functional equations, and you can say these really cleanly in the spherical case. They're just ratios of zeta functions, like what you have in Harshchandra's C function, but globally. Langlands defines a constant term formula, and the constant term determines the growth rate. It's a straightforward fact. So if you understood this formula in general, you might say, okay, I could just pick off which terms are growing and which aren't. The problem is they cancel each other. The lambdas that we look at are stabilized by non-trivial subgroups of the Weil group, and you can have a pretty ugly mess of combinatorics to sort out. And in general, these m's aren't scalars that are intertwining operators. So Langlands introduced a criteria for a residue to be L2. And that just simply has to do with which exponents survive. Basically, the term itself has to be square. The piece of the constant term itself has to be square integrable for each such term. So I don't want to go through the maybe all the details because I actually spoke about this already at Weizmann. There are some tricks you can do in the spherical case to deform along a certain family, which cuts down the size of the computation by like a factor of 1,000. And then you can almost do it by hand. I mean, at least in some cases. Most of these intertwining operator type things, which are scalars here, vanish. Joe and I weren't able to do that. I'll come back to that in a second. So I kind of just mentioned this by words. The three smallest representations come up very easily this way from string theory also. And maybe these other orbits were going to show up in string theory. Sorry, I just want to come back to this slide. I have them out of order. So Hundley and I have to control the intertwining operators. Also, so there are normalized intertwining operators, and one needs to be very careful about where they vanish and where they're holomorphic and do all sorts of deformation arguments. But after that, it can be written down in a way that's basically ends up in combinatorics. So I want to highlight at the bottom that you have a certain Weil orbit with maybe some signs on it, and you're sort of averaging some polynomials basically over the Weil orbit. And you want to show these are zero. And so that is telling you that from the point of view of averaging small degree polynomials, they're indistinguishable from spheres. That's a topic called spherical designs. And so this is related to sphere packing, for example. It's a well-known subject. And so at the end of the day, the way unitarity is settled is to move the problem to through an analysis of intertwining operators to this combinatorics. Okay, so let me go back to the previous one. I just had these out of order. So there's a picture here I again stole from Jeff. I don't know even why I bothered because you can't read a thing, but this is a diagram of all the orbits for E7 or E8. I think there's 70 of them, and it depends what's top and what's bottom. But basically, the work that's been done in number theory so far has been on the trivial representation and the minimal representation, and then string theory brought in the next to minimal representation. So there are these three here, and then other string theorists started poking around here for various reasons to look at higher correction terms and graviton scattering. But there's a whole rest of the picture here. Now, if you get to the very top, you get to generic, but there's all these things here, and there's hundreds of interesting unitary representations here, presumably, which have automorphic realizations. And that's got to be cool. I mean, there's got to be something really amazing we can get out of that. And I hope that the future will hold some great progress in that. So where we stand, we have all the unipotent representations now. We want to finish showing their unitary, and that should be a major benchmark towards the unitary dual problem once that's done, if it's done. And hopefully then that will help get more progress in the unitary dual problem as a whole, because we'll have more building blocks to work with. I mean, this is still highly speculative and questionable. And it's at that point, then you can ask the question of how difficult will the rest of the unitary dual problem be? I really don't have any idea, but certainly a lot more should come out of this, and it could be that it's just a lot of combinatorics rather than a lot of representation theory at that point. I'm just speculating, and there are people watching who know much more than I do, but I think these are interesting questions. And we should get some really highly interesting new automorphic forms, hopefully by highly interesting new people brought into our community mathematicians. And hopefully we'll get some more ways to study these and see why they're important in different subjects. I probably rushed too fast at the end, but let me close with an optimistic quote of Nolan Wallach in one of his books. And I hope this will happen. I hope we'll see volume 3. This is referring to his books. He has 2 volumes on real reductive groups. Okay. So, Dima, thank you for hosting me in Rehovot. I hope to see you soon there. And hope everyone stays healthy and wish you all the best. And hopefully we can all rise to all the challenges we have. And I know we can do it. Except for the unitary part.
Thank you for your talk. Questions, please. So I have a question. Is the uniqueness of next to minimal representations known for some groups?
Yeah, some groups it's minimal. So, no, but no, I don't think so.
I mean, for some groups it's false, like DN or EN, but...
Well, actually, come to think of it, I guess, I mean, you could ask if you know the Arthur packet is a singleton, you could say the minimal is the unique one among those with a certain infinitesimal character. But I don't know how to rule out in general there being some wild ones which just somehow have the same small wavefront set. I don't understand that, but if there's a point of view, I mean, I think David knows a lot more than I do about this, but if there's some point of view that you can build other representations out of unipotent representations, and then say something about the wavefront sets based on what you've built out of, maybe there's some hope of that. But like you say, this is something which you don't expect to be true in general. I mean, generic is certainly false, right? Many representations are generic. So.
Steve?
Yeah.
Thanks very much for the interesting lecture. So you mentioned that this is a non-trivial question about which representation in the unipotent Arthur packet are local components of residual representations, right?
Yes. Yeah.
So there is a description, right? There is a result of Langlands for classical groups. That
you're right. I should have mentioned that.
Can be described through Springer correspondence, right?
Absolutely, yeah. I've been so focused on
I don't know. I've seen in Kim's paper written this as a conjecture for all the groups, including exceptional. First of all, do you think this conjecture seems true now? Because the paper about G2 of Kim was written many years ago, so I don't know if there are more insights about that, and whether you believe that the same is true for real groups.
So as far as the Kim statement, maybe actually one of the series of papers, which I think maybe you're a co-author on even, I remember there's a very interesting discussion about the other implications of the statements he predicted. And I'm not sure. I'm very confused by the status of that. There's some plausibility to it. And one plausibility is that, I mean, for example, Atlas can tell you one way to look at it, one thing we could do is Atlas has a command cuspidal data, which tells you how it's induced as a real representation. And if you run it on this item 2 I had earlier, so I can get it back up. It'll take me a little while to find the slide. I have to re-enable screen sharing, sorry. Okay, so if you run that on this cuspidal data on here, which in fact I have in another window, I have it open even. Okay, you see this here?
Mhm.
Okay, so this command tells you for that representation that, at least in terms of real groups, it really doesn't seem to come from induction from any proper Levy. And that's a bad sign if you want to make an Eisenstein series residue. So so I think you could get evidence for it, but I don't have a firm grasp on this.
How is it possible not being part of any induction? I'm confused.
Oh, this is the one that's tempered. Yeah.
It's not induction of anything temporal.
Yes.
Okay.
Well, I mean, actually, I mean, Jeff or David, can you bail me out of it? I just learned how to use this command yesterday. I'm not sure exactly what it's saying. It's a good chance to advertise Atlas.
Yeah, right. Tempered representation are not supposed to be in the residual spectrum. But hold on, is it possible then? The Arthur packet, as in PID cases, can contain both tempered and non-tempered representations, right?
Yeah, I think that's in this picture I had before, which which I learned from you and your collaborators.
Thanks.
For real groups, tempered representations are pretty simple, and this Steve's representation number 2 is a limit of discrete series representations for G2. But that prevents it from appearing in a sort of non-trivial way as the Langlands quotient of something else, but it doesn't prevent it from appearing inside another, well, induced in Eisenstein series. So I'm not.
Just
I don't
not as a
understand.
residue, right?
Well, actually, let me ask you. I'm a little confused about this myself. I mean, there's an expectation that tempered shouldn't show up as a residue. Is there a proof?
This is for sure.
Yeah. So remind me the proof. I just don't remember. I think I saw this many years ago.
It's about the automorphic exponents. If you're an L2 automorphic representation and you have a tempered component and you're cuspidal, you cannot appear in the residual spectrum.
Oh, I see. So it's just simply okay. I'm not sure I completely see that, but I'm sure you can. I'll email you later, and you can.
It's an old result of Wallach, actually. For
that sounds right.
Yeah.
Okay. Thank you, Harold.
You're welcome. Thanks for the nice lecture.
Yeah. Okay. I'll ask you about this later. I'll write this down. No, but this is sort of a freak example in a way. I mean, it doesn't. I mean, you don't. It's not like you're going to get a lot of free unitarity results in general. That it's tempered, so it's unitary. I mean, it's on G2 and maybe once more in F4. Now, Jeff Adams actually ran a calculation to look to see if there are other examples of it.
I mean, already for SL2, if you look at a limit of discrete series representations, that appears in a continuous, as part of the continuous spectrum in Eisenstein series. If you look at the non-spherical principal series for SL2, you get perfectly good Eisenstein series in that way, and you get a continuous family, and at 0 you have this limit of discrete series representation appearing there, not cuspidal, not residual, but
well, even the spherical one, I think, but there could also still be. There's another question which is related to Nadia's questions. Do you also have cusp forms living at the same place that are Eisenstein series? And that does happen actually in that case sometimes. There's no contradiction with what you said at all.
I'll just chime in here with one other comment about that, which is if the group is not quasi-split, there seem to always be examples of Arthur packets which consist entirely of tempered representations. So in this packet you found here, it had both tempered and non-tempered. But for a non-quasi-split group, there are examples where the entire packet is tempered, which to me is extremely surprising.
In addition to the obvious one where the parameter is 0, you get everything tempered. Yeah, so I mean, if I had to summarize this lecture on 1 foot, as we like to say, there's like literally 1,000 new representations here to look at, and they're really interesting.
Steve, there is a question in the chat. The following one. We can think about one side of local Langlands as a category of coherent sheaves on L parameters. How does the analogous version look like when considering Arthur packet instead of L packet?
I have no idea. I'm sorry.
Any further questions?
This is a favorite topic. This is sort of what the book with Adams and Barbash from 1991 is about. Well, I don't have a short answer, but when you're looking at geometry, at perverse sheaves related to L parameters, then perverse sheaves have sort of, what's the word, associated variety kinds of parameters. There are things in cotangent bundles where the perverse sheaves are living, and the Arthur parameters amount to, well, it means you're looking at some perverse sheaves on the L parameter spaces where these associated varieties contain a particular piece that's given by the Arthur parameter.
Thank you very much. Any further question? If not, then let us thank Steve again.
Let me thank my collaborators for giving a non-trivial part of the speech to talk to. Okay, so Lashana Haba be'Eretz Yisrael.
Lashana haba b'Yerushalayim ha'briah.
Okay, take care, everyone. Stay safe. Do good things.
Take care.
Okay, bye-bye.